All right, let's talk about unlocking a certain kind of calculus problem, one that can look totally impossible when you first see it. And the key isn't some brand new complicated rule. Nope, it's a tool you've actually had in your back pocket all along. Trigonometry. You know the feeling, right? You're looking at an integral, it's packed with powers of sine or products of cosine, and, well, none of your usual integration tricks seem to work. It's like you've hit a total mathematical brick wall. So what do?
Well, the secret weapon isn't some crazy high-level calculus theorem you haven't learned yet. It's something you already know, your trigonometric identities. These are the tools that are going to help us completely pull apart these tangled-up problems and solve them.
So here's our game plan for this explainer. First, we'll tackle integrals with powers of trig functions. Then, we'll move on to products. After that, we'll see how these exact same ideas are used to build some of those fundamental integrals you probably had to memorize. And finally, we'll wrap up with a super important insight for your next exam. Let's dive in.
Okay, Section 1, Integrating Powers. This is all about what you do when you see an exponent on a sine or cosine that just stops you dead in your tracks. You know, something like sine cubed x or cosine squared x.
Let's start with this classic example, the integral of cosine squared of x. Now, you might be tempted to try the power rule, but remember, that only works for something simple like x squared, not a whole function like this. So as it stands, this integral is basically stuck. How do we get it moving? And here's where the magic happens. We use an identity, specifically the power-reducing identity for cosine. We're just going to swap out cos squared x with 1 plus cosine of 2x all divided by 2. And just look at that. The exponent is completely gone. We've totally transformed the problem. By making that one simple substitution, our tricky integral becomes, well, a whole lot easier. It's now the integral of 1/2 plus 1/2 cosine of 2x. And just like that, we've got a simple sum that we can easily integrate piece by piece. The problem that was impossible a second ago is now totally doable. Okay, so that worked great for an even power. But what about an odd one? Let's dial up the difficulty just a little bit and look at the integral of sine cubed of x. For this one, we're going to need a slightly different, but just as powerful, strategy. Here's the playbook. Step 1, we split that odd power. We rewrite sine cubed x as sine squared x times sine x. Now, why would we do that? Because it leaves us with a single sine x to work with. Step 2, we use our old friend the Pythagorean identity to change sine squared x into 1 minus cosine squared x. Now look at what you've built. The integral is now perfectly set up for a u substitution. If we let u equal cosine x, its derivative, negative sine x, is sitting right there waiting for us. Beautiful.
Awesome. Let's keep building on this and move to Section 2, Integrating Products. Here, the idea is to take a really difficult multiplication problem and, you guessed it, use another identity to turn it into simple addition or subtraction, things we can actually handle.
So, take a look at this one, the integral of sine of 2x times cosine of 3x. Just like before, trying to integrate a product like this directly is a major headache. But thankfully, we have another special tool for exactly this situation. The tool for this job is a product to sum identity. It lets us turn a product, like sine A times cosine B, into a nice sum of other sine functions. In our problem here, A is just 2x and B is 3x.
So when we plug that identity in, our integral completely transforms. The nasty product becomes 1/2 times the integral of sine of 5x minus sine of x. And there it is again. We turned a hard product into a simple difference. And integrating this is now a piece of cake.
All right, let's head into Section 3, the fundamental 4. Now, you probably had to just memorize the integrals for tangent, cotangent, secant, and cosecant. But did you ever stop and wonder where those formulas actually come from? Well, it turns out they're built using the exact same ideas we've been talking about. So for our example, let's just pick one and derive the integral of tangent of x. You might have the answer memorized, but seeing how it's built is actually really cool. And it all comes down to a clever substitution. Honestly, the logic here is surprisingly simple. First, you rewrite tangent as sine over cosine. This structure is just screaming for a u substitution, right? We let u be the bottom, cos x. That means du is negative sine x dx, which is pretty much exactly what we have on top. So the integral becomes the negative integral of 1 over u, which gives us negative natural log of u. Then you just substitute back, and you get negative natural log of cosine x, which, using log rules, is the same as the natural log of secant x. And there it is, a standard formula you probably memorized, derived from scratch. And that brings us to our final and maybe most practical section, your exam insight. So why is this topic so popular on calculus exams? What are your professors really trying to figure out when they ask you these questions? Here's the inside scoop. These problems are just super efficient. In one single question, a professor can test two completely different skills at the same time. First, do you actually know your trig identities from memory? And second, once you've used the identity, do you know which integration strategy, like U substitution, to use next? It's a 2-for-1 test of both your trig knowledge and your calculus strategy.
So this brings us to the most important point of all. The real goal here isn't to go out and memorize dozens of new, specific formulas for every possible trig integral. No way. The real key, the strategy that unlocked every single problem we looked at today, is just getting comfortable and fluent with your core trig identities. They are the real keys to the kingdom.
So, as we wrap this up, I'll leave you with a question to think about. What other really tricky-looking integrals, maybe even ones that don't involve trig at first glance, could be cracked wide open with just the right identity? Because this whole idea, this power of a clever substitution, is something you're going to see again and again.